So we're going to start with meaning and then progress all the way down, if you will, down to the level of physical sounds. So the study of linguistic meaning is generally referred to as semantics. And this is a misunderstood term. So I think a lot of people who have never taken a linguistics class think of semantics as being sort of arguing and nitpicking over little tiny distinctions of wording. It's actually extremely frustrating to people who do formal semantics that everybody uses the term that way. In any case, that's the way it's often used in English. Within linguistics, semantics refers to the study of meaning, right? And so here's kind of a central question of semantics. What kinds of meanings can language convey? And that's obviously a very, very broad question. And the answer is, a nearly infinite variety of different kinds of meanings. Within generative linguistics, most work in semantics is going to fall in the area of formal compositional semantics. And this is actually not something that we have any specialists in here in the department. But it's still something you could potentially study or investigate. So both, all of our core linguistics faculty know something about formal semantics, even though it's not our primary specialty for any of us. So formal compositional semantics studies really a very small piece of the puzzle here. It's not studying all kinds of meaning. It's zeroing in on a particular kind of meaning that many semanticists think is particularly germane for study, basically, that it's easier to study than other kinds of meaning. And so one of the things you know when you know the meaning of a sentence is what the world would need to be like in order for the sentence to be true, right? Arguably, this is something that you know just about every time you hear a sentence in a language that you understand. So you may not know whether the sentence is true or not, right? Often you don't know whether something you're hearing is true, but what you do know is what the world would need to be like if it were true. And so this is referred to as truth conditional meaning. It is absolutely not the only kind of meaning that's associated with language. There's all other kinds of meaning as well, but this is the one that's the subject of formal compositional semantics. It's truth conditional meaning. So here's a kind of central idea from formal semantics. Humans are able to compute the truth conditional meaning of any well-formed sentence in their language, even those they've never heard before. So at a first pass, there's an infinite number of possible sentences in your language. You've never heard many of them before, yet whenever somebody utters a sentence that you've never heard before, you usually understand what they mean. Again, you might not know whether it's true or not, whether it's right or not, but you understand what the world would need to look like in order for a sentence to be true. And so the question is, how do humans do this? Right? Because a very naive view of semantics would just be, well, you hear sentences in your language and you learn to associate them with meanings, and then when you hear them again, you know what they mean because you've memorized it or something like that. The fact that we can do this with a potentially infinite number of new sentences we've never heard before shows that this is not about memory. It's about some kind of a system of rules or constraints or generalizations. So here's another central idea, and this one is kind of the centerpiece of formal compositional semantics, and it is accordingly called the principle of compositionality. The meaning of a complex linguistic expression is a function of the meanings of its parts and the rules for combining them. So this is a potential answer to the question of how do humans compute meanings for an infinite variety of novel sentences. Well, the first claim here is that it's a function, right? So it's a way of mapping any number of things to any number of other things. This is why it can take potentially infinite variety of novel inputs and still be able to output a meaning for them because it's a function. It's a systematic set of principles or rules for constructing meaning from linguistic expressions. What is that function going to involve as inputs? Well, at a minimum, we're going to need to know the meanings of the parts, which are going to be morphemes, right? Or maybe words, if that's simpler to think about. So you know what the words of your language mean. And then when you put them together, there's going to have to be certain rules for combining the meanings of those parts. Right? This is the principle of compositionality. It's the idea that you can build more complex meanings by having a system, a set of rules, a function, from the smallest bits of meaning that you have in your language, basically morphemes, and certain rules for turning the meaning of more than one thing into a new meaning that incorporates both. So taking the meanings of the parts and some rules for combining them and getting out of that a complex meaning for the whole linguistic structure. This is the basic sort of presupposition of linguistic semantics. So that was a very high-level abstract summary. What does this actually mean? Like, what kinds of things do semanticists study? Well, here's a classic example, and some of this material is taken from my colleague Hadass Kotek, who's a semanticist, and helped prepare these slides. Here's the example I'm going to use here. What do English quantifiers mean? And quantifiers are a topic that semanticists have been very interested in for the last 50 years. And you'll see why in a minute. They have a sort of interesting logical structure to them. So first of all, what is a quantifier? Well, syntactically, it's a kind of determiner. It's the kind of thing that attaches to a noun and makes a noun phrase, or sometimes it's called a determiner phrase. And it basically picks out some relevant nouns of the kind that it attaches to. So these are words like some, as in some boys, or every, as in every girl, or most, as in most dogs, or three, or more than half, and so on and so forth. There's lots of these quantifiers in English, and as far as I know, every other language that's ever been studied has at least a couple quantifiers as well. They seem to be a category that's present in just about every language, although, you know, depending on how you define quantifier, it can be a little bit tricky to try to argue about whether something is a quantifier or not. But I think you get the basic idea of what a quantifier is. So what do they mean? Well, let's take a look here at some boy danced. So what is this expressing? Well, often formal semanticists will think about the meaning of determiners in terms of belonging to sets. Right? So what is a set? Well, it's just a group, possibly empty group, of things. Right? And so in this case, the meaning of the word boy is going to be something like the set of all the things in the world that are male humans, or something like that. And the set of the meaning of danced is going to be something like the set of all the peoples in the world who dance, or something like that, or who danced at the past tense. And if you think about that in these sort of simple terms, right? So we've got things that are boys and things that danced. And what some is doing here is naming a relationship between these two sets. Right? And in particular, in sort of formal logic terms, this would be phrased as the intersection of the set of boys and the set of dancers is not empty. There exists something that is both a boy and danced. Right? So that's in sort of formal logic terms. These are often easy to think about in terms of Venn diagrams, which are these sort of overlapping circles here. And so you can think of circle 1 as being the set of all boys, and circle 2 here as being the set of all things that danced. And what the quantifier is asserting here is that if you take the overlap, this little area in the middle here, between the things that are boys and the things that danced, there exists at least one person in there, or at least one thing in there. Some boy danced, right? So that's a way of thinking about the meaning of quantifiers, is that they name relationships between sets. Okay, so far so good. What have we learned from this? Doesn't seem that interesting yet. Well, let's keep going a bit. We'll do a couple more examples. Before we get there, important property here. We're going to ask for each of these quantifiers, right, do they place restrictions? So, all of them are going to potentially place some restrictions on the overlap between two sets. In particular, in this case, the sentence can only be true if this intersection, right, the overlap between these two sets, has a certain property, right? So the meaning of the quantifier cares about this area in the middle. We can equally well ask for each of these quantifiers, does it care about this area in set 1 that isn't in the middle, isn't in the intersection? And does it care about this area in set 2 that isn't part of the intersection, that isn't in the middle? So we're going to ask whether quantifiers put restrictions on those. Right? So we already saw in the last slide the intersection between the two sets. The quantifier sum definitely puts a restriction on this one. Here's some questions about the other two parts of this universe here. Can there be boys who are not dancers? Is it okay for somebody to be in here? And with some boy danced, yes, that's fine. The quantifier doesn't really care at all. Right? How about over here? Can there be dancers who aren't boys? If some boy danced, is it possible for there to also be dancers who aren't boys? Sure, absolutely. So this quantifier also doesn't seem to care about this area over here. So this one seems to only care about the stuff in the middle, doesn't really care about this, doesn't really care about this, doesn't put any restrictions on them. Here's every boy dance. This is sometimes referred to as a universal quantifier. And here, rather than talking about the intersection between the two sets, this is going to say that the set of boys, this little circle in here, is a subset of the set of dancers. In other words, it's fully contained in this larger set of things that danced. So still a relationship between sets, but this one's a little bit different. I mean, of course it is. It's a different word. It has a different meaning, right? So the relationship between sets here is a different kind of relationship. This is notated in set theory, in mathematical set theory, with this subset or proper subset symbol, but that's not super important. Just means that this set is wholly contained in a larger set. That's what every boy danced means. The set of boys is a subset of the things that danced. We can ask again about these different areas in the whole Venn diagram here. So here's the overlap, the intersection. It happens to be the entire set boys. Here's some questions. Can there be boys who are not dancers? Can you have a boy over here? Oh, excuse me, that's wrong. Can there be boys who are not dancers in this picture? No, there can't. There's not even a place to put them because the boys are wholly contained in this narrower set. So it looks like every, as a quantifier, cares about that first set of boys. Right? And it certainly cares about the overlap between the two sets. What about dancers who are not boys? If every boy danced, can there be other dancers who aren't boys? Yes, yeah. So every actually doesn't care about the area of the danced set outside the boy set. It, again, doesn't seem to care about this area. Now, why do I keep doing this with does the quantifier care about this? Does it restrict this? Does it restrict that? Well, we're going to reach some interesting conclusions in the end, and this is going to be important for that. More generally, why do quantifiers work the way they do instead of working some other way? And this is what I've been pointing at with this idea of restricting different sets. Right? This is the property known as conservativity. Right? So if you have a structure like quantifier set A, set B, like every boy danced, right? We already saw that for some boy danced, we're saying that that's true if and only if the intersection of the set of boys and the set of things that dance is not empty. That's what this, again, set theoretic notation is trying to express here. This little double arrow is a logical entailment. It means if and only if. Right? So some boy danced, if and only if, set of boys, and the intersection with the set of things that danced is not empty, if there exists something in that intersection. Here's, at a first pass, 3 boys danced. Right? So the meaning here is going to be something like these vertical lines mean the number of things in the expression in between. It's called the cardinality. So this one says that the number of things in the intersection of boys and danced is going to be equal to 3. That's what it's saying. The things that are both boys and danced are 3. 3 boys danced. More than half of the boys danced. This one's a little bit more complicated. And so here, it's definitely putting conditions, again, on the intersection between boys and things that danced. So all 3 of these have something to say about the intersection of boys and dancers. This one is the same, but here you need to compare that intersection to the things that are just boys that did or didn't dance. Right? And the set of boys that danced has to be more than half as large as the number of things in the set of just boys in general. So this is a quantifier that cares, yes, about the overlap, the intersection between the two sets, but also about the entire rest of the first set of boys. Here's one, no boy danced. This one says, again, the intersection of things that are boys and things that dance here is equal to the empty set. That is, it is empty. So here, some boy dance, we saw that it's supposed to not be empty. No boy dance is a lot like that, except here it just is empty. And finally, every boy danced. Well, the entire set of boys is a subset of the entire set of dancers. Right? So here's the kinds of things that you get in quantifier meanings. And what does this have to do with the conservativity property? Well, what does conservativity mean? In a structure of this sort, where you're quantifying over two sets, set A and set B, right, boys and dancers, all the determiners that we've seen so far put some restrictions on the members of set A. Right? So, we saw one where we cared about the entire set of boys. All of them seem to care about the intersection between boys and dancers. But so far we haven't seen any determiners that put special conditions on all of set B, on all of the dancers, right? This is what I'm getting at when I keep saying that the quantifiers care about this part, some of them care about this part. So far, none of them have cared about this part at all. Right? So, for instance, we haven't seen any quantifiers that put restrictions on the entire set of everything that's a boy or a dancer. We haven't seen anything like that yet. And one can imagine quantifiers that wouldn't have this property, right? So out of the ones we've looked at, the real quantifiers, none of them seems to care about the members of set B here, the dancers. But it would be easy to think of a fake quantifier that would do exactly that. So this one's going to be basically every non or something like that. That's going to be what we're attempting to say here. And we're going to call this fake quantifier blarg. Right? So this fake quantifier would say if blarg boy danced, then it would mean everybody who isn't a boy danced. In other words, this one would care a lot about the set of dancers. It would put strong restrictions on the set of dancers, namely that everybody who isn't a boy is contained in that set of dancers, but far few or really no restrictions on the set of boys. Right? This says something about the set of people who danced and aren't boys. This quantifier doesn't care about what the boys did. It only cares about what the dancers did. That would make this non-conservative. So conservative quantifiers are the ones that only care about their first argument. This fake quantifier is non-conservative. It only cares about its second argument and doesn't really care about the first. So this is my made-up quantifier. The interesting fact about conservativity is that quantifiers like blarg don't exist in English, and they don't seem, as far as we can tell, to exist in any other language either, at least not the ones that have been studied by formal semanticists, and that's a lot of languages. Another way of stating conservativity is that natural language determiners only care about elements that satisfy their first argument, right? Boys and all the examples that we've been looking at. A determiner is conservative if and only if quantifying over argument 1 and argument 2 is the same as quantifying over argument 1 and the intersection of argument 1 and 2. This is a little bit complicated in logical terminology. It's basically a way of restating what we've just looked at in the last few slides. And basically it's saying that in terms of their second argument, B here, the dancers, conservative determiners only care about that second set to the extent that it's inside the first set, right? In other words, they don't really care about the second set at all, except for the ways in which it relates with the first set. So another way of sort of rephrasing this in intuitive English would be to take that second set here, every boy danced, where danced is the second set, and replace it with the intersection of the two sets. In other words, every boy is a boy that danced. So if you can make this pattern of inference, then it's conservative. And if you can't, then it's not conservative. This is a sort of slightly more intuitive test to see if a quantifier is conservative. Every boy danced, right? Does that mean that every boy is a boy that danced? Absolutely. Some boy danced. Does that mean that some boy is a boy that danced? It does, right? Now here's our non-conservative fake quantifier blarg, right, which means every non. What does this one do? If every non-boy danced, is it true that every non-boy is a boy that danced? It is not true, right? So that is in fact false, totally false. So this is a non-conservative determiner because it's doing a funny thing to this set boy, or really not restricting that set at all, and so this pattern of inference doesn't go through. This is what a non-conservative determiner looks like. So this is, I'm not going to be able to tell you right now exactly why conservativity seems to hold in natural languages. There are a bunch of ideas out there about why this holds, but this was more meant as an example of the kinds of problems that formal semantics looks at. Right? So we have different elements here. We're describing language-specific meanings in English. What are these particular linguistic items like in English? What's the structure of the sort of semantic space in which quantifiers operate? What's the fine-grained mathematical structure of the kinds of relationships they denote? And then there's also this much broader question of why do linguistic determiners seem to have this formal logical property and not some other formal logical property like non-conservativity? These are the kinds of questions that semanticists might be interested in. And of course, these quantifiers and conservativity is just one example of a topic that semanticists have been interested in. There's many, many more. So next up, we'll look at syntax.